Welcome to another video on Joe's Physics Corner, and today we're going to solve the Brachistochrone problem. And I'm going to divide the video into 4 parts. And the first part is going to be the introduction to the Brachistochrone problem and an introduction to a cycloid, a shape called a cycloid. The second part will be deriving the time function of the system that we are talking about in the Brachistochrone problem. And then we're going to talk about the Beltrami identity and how it links to the time functional and in terms of minimizing the time taken. And finally, we're going to insert the time functional into the Beltrami identity and solve the Brachistochrone problem. So first, part 1, introduction to the Brachistochrone problem. So what is the Brachistochrone problem? Basically, the Brachistochrone problem is deriving the shape of the path that an object should take if it wants to minimize the time taken for it to fall. Let's say we have a Cartesian plane like this, and we want this object that starts from the origin to go to an abstract point here called x1, y1. This is the x-axis and this is the y-axis. There are infinite ways of this object, the infinite number of paths that this object could take in order to go to this point over here. It could be a straight line. It could be something that looks like this, something that looks like this. And we can even give equations to these lines and say, well, maybe it could be a parabola, or maybe part of a sine function, or a circle with a set radius from this point, or whatever. And the point is that there is only one path that gives the shortest time, that gives the shortest time of descent from this point here to this point here. And now you may think that, because time taken is distance divided by speed, when you have the shortest distance, aren't you going to have the shortest time? And so isn't the shortest distance between this point and this point, which is a straight line, our answer? And the point is that it's not necessarily the case that a straight line will give the shortest time. And in fact, it is never the shortest distance between a point and another point is always not the answer to giving the shortest time for an object to move from a point to another point. And I would like to start off by telling you what the answer is. And the answer is, in fact, it will look something like that. And now this curve has a special property, and the property is that the path here is in the form of a cycloid. And so before we derive derive the equations of paths, and in conclusion prove why it is in the shape of a cycloid, I'm just first going to tell you what a cycloid is and derive the equation of a general cycloid. So what is a cycloid? Well, cycloid is basically the path that one point in the circle will take if we are to roll this circle. And so let's say the circle starts here. Maybe a second later, it's here. The circle has rolled into this position over here. And the dot here, the fixed point here, has now moved somewhere over here. And the next timestamp, it has moved to here. And the next timestamp, it would have it has rolled this amount of displacement, so it's going to be here. And finally, it's going to go back to its original position over here. A cycloid is basically what is shown when you link all these dots together. And what I've drawn here is an imperfect shape because the distances here are not kept the same. But what you're gonna get what you're gonna get as a shape of a cycloid is gonna look something like this, whereby the point at its maximum y displacement is here, and it's gonna start somewhere over here. How are we gonna get an equation of this line? Well, let's draw another Cartesian plane and draw a circle that looks something like this. And this circle is basically, this is a timestamp. This is a picture taken. Imagine this as a picture taken in a certain timestamp. And you imagine the circle at its original position was here. And so when we say this point, the fixed point that we're tracking its trajectory as P, we know that, let's say that the circle has started on the origin. So P was at the origin at time equals 0. And at time equals whatever, time equals 1, 2, whatever time it took for the circle to go to this point over here, this position, the fixed point P has moved from the origin to this point over here. This means that when we define the x-coordinate and the y-coordinate of P, we could basically get the equation of a cycloid. Now, how do we do that? Well, first, let's set some important points that we're going to use. Maybe I'm going to draw this a bit bigger. So we said that we have a Cartesian plane. We have a circle. We have the origin. We have P here. It should look something more like a circle, so yeah. We have P here. Let's say we have this point here that touches, that is right, that forms a perpendicular line with the x-axis. Let's say that is I. And let's say the center here is C. And let's say we have a line that's perpendicular over here. And let's say that's as anything really. Let's say that's Q. And then let's say this point here that forms another perpendicular cross that is down, right, horizontally, vertically down from point P as H. Now we just said that if we define the x-coordinate and the y-coordinate of point P in terms of some variable that changes, we have basically defined the equation or the function of a cycloid. Now, we need, as I said before, we need something that we have to change. And it can't be x or y, because then it will make the problem even more complicated than it should be. And so let's imagine the circle. Let's imagine point P going back to the origin and the circle rolling to the left at this point over here. Something like this. A circle with a vertex on the origin, with a point on the origin, a tangent, which is point P at time equals 0. And let's imagine a circle. Then we have this angle over here is going to be 0, because line CP would be identical to line CI, which are both the radiuses of the circle. And so we could say that because the angle between CP and CI starts at 0, we could say that this is theta. And say that in terms of, we could define the equation or the coordinate of P in terms of theta, and then we have the equation of a cycloid. Now, how do we do that? Well, let's look at the y-coordinate of P first. So the y-coordinate of P. Well, that's going to be equal to the length of PH. PH is going to be our y-coordinate, basically, because it's the height from y equals 0 to y equals whatever, and it is the vertical displacement from the x-axis. And so how do we represent PH in terms of the variables that are given? Well, we know that pH is equal to Ci minus Qi. So let's write that down. And we know that Ci is basically R because it's R from the origin to the tangent point. And so we have R minus Qi. No, wait, it should be CQ, right? Yeah, CQ. Because it's Ci minus this, and we get this length over here. And what would CQ be equal to? Well, CQ is the adjacent side of theta, of the center point, and so we can say that it's equal to R cosine of theta. This gives us the y-coordinate of P as R times 1 minus cosine of theta. We could do the same thing for x. Well, x is a little bit more complicated. So x is basically OH. OH is our x component of P. And OH we know is equal to OI minus HI. So first of all, let's write that down as we did for here. And we need some expression that gives us OI. What would OI be equal to? Now OI, it's kind of hard to imagine, but let's go back to the timestamp time equals 0 and imagine how the circle was like that. We said that P would be touching O, and it would have rolled like that so that P reaches O. This means that whatever distance the circle traveled from timestamp 0 to whatever timestamp that's being shown here, that distance that the ball moved, that the circle moved, would be equal to the arc length from P to I. Because a circle travels like that by rolling from one arc to by rolling in a circle. And so the arc length is basically the distance will be equal to the distance that the circle has traveled, which is OI. And so we could say that OI, this should be OI, sorry. We could say that OI minus HI, so OI, we said, is equal to the arc length. So we could say that it's equal to the circumference times the 2 pi over the angle, because we're giving theta as a radian, minus HI, which is the opposite side, so it's going to be R sine of theta. Now this would give us, cancel these out and say R theta is equal minus R sine theta, and so it is going to be equal to R times theta minus sine of theta. And basically we have given with two different expressions, one in terms of y, and one that gives the y-coordinate of P, and one that gives the x-coordinate of P. We have now the equation for the cycloid, whereby you could say that the coordinate P, which gives the path for a cycloid, would be equal to x, which is R of theta minus sine theta, comma R of 1 minus cosine theta. Now, you have seen my content, so I'm just going to erase this. And I'm going to leave this expression, this equation, or the point coordinate of the path of a cycloid. I'm just going to leave it here. I'm just going to leave it here for future reference. And I'm going to move on to part 2 of my video right now. Now moving on to part 2, which is the time functional of the Brachistochrone system. Alright, we're going to get the time functional of any object that is following a path. And so let's draw, first of all, let's draw the system we're going to use in solving the Brachistochrone problem. So as mentioned before, we have the origin over here, we have the x-axis and the y-axis, and we have a point its coordinates x1, y1, and we have a path, any arbitrary path that could look like anything as absurd as this, that starts from the origin and ends at x1, y1, and is continuous. And there is a constant effect of gravity that is acting on the system, the object that is falling. And so how do you define time? So the time functional basically means defining time in the form of a functional. A functional being a function that has multiple variables, and so it depends on a function itself. And so how do we get time? Well, from basic physics, we know that time is equal to displacement over velocity. This is, well, you could imagine, dvt, triangle diagram, whatever, but this is fact that time is equal to displacement over velocity. And so if we have an expression that gives us the displacement and an expression that gives us the velocity, we could get what the time would be. So I'm just going to write t is equal to s over v down. And how do you get s, the displacement at any point in the path over here? And the displacement here would basically mean the length of the path. And so how do you get the length of a path that may not necessarily be composed of straight lines and would most definitely be in the form of a curve? Well, let's zoom. We did a similar thing in the previous video, talking about the Euler-Lagrange equation, and we did the same thing. We zoomed a certain part. Let's zoom this part, and we're gonna get a straight line. We're always gonna get a straight line if we zoom in infinitesimally into a certain part of this path, and we could divide that small displacement called d of s. We could divide it into two components, dx and dy, and we have the expression from this that gives, due to Pythagoras' theorem, we get ds squared is equal to dx squared plus dy squared. Okay, and then we could say that ds is equal to the square root of dx squared plus dy squared. And what we want is s. And so we could integrate both sides and say that s then from 0 to x1, because this point here is x1, it could be y1, but it really doesn't matter. What we are interested in is saying that it's from 0 to x1, adding all the small ds's together. And we didn't like this because we want dx at the end, because that's the form we are used to do. And so we could say that it's equal to 1 plus y prime squared times d of x. Y prime squared is just a dy over dx total squared, because we're taking dx out of the root. Alright, so we have an expression of s in terms of x, y, and y prime. And therefore it is in the form of a functional. But still we didn't define time yet. We have to define time. And for time we said we need both the displacement, which is this, and the velocity. And so how do we get the velocity? Well, we could get velocity in many different ways, but the easiest way I can think of, this has to be here. The easiest way I could think of is giving velocity in terms of the energy change. So what do we know about energy change? We know that, let's say that the velocity at the start is 0. So at the start, the object is not moving. And from that we can know that the total energy of the system has to be equal to 0. Because at the start we say there is no kinetic energy and no potential energy. And we're saying that when we're talking about potential energy, we're giving it in terms of, we're saying that potential energy at here, at the surface, at the origin is 0. And so we could say that energy total must be equal to 0 at any point in time, because due to conservation of energy. Okay, then what would be velocity? Let's say the object has moved down this path and is not currently at this point over here. The object here would have two types of energy. It will have kinetic energy, which we could give as 1/2 mv squared, and it will also have gravitational a change in gravitational potential energy. And that change in gravitational potential energy would be equal to negative mgy, because its gravitational energy is decreasing from this point to this point. Although we have said that gravitational energy here is equal to 0, still we could say that it has kind of a negative value of the gravitational potential energy, because it is changing from a inclined point to down. And so you could say that 1/2 mv squared minus mgy, so kinetic energy plus potential energy, which has a negative value, is also equal to 0. And then we could say that, well, we could cancel the mass out and say v squared is equal to 2 times minus gy, so plus 2gy. And so v is equal to the square root of 2gy. Okay, then we have v and s, so therefore we have the time functional we have the functional that defines time at any point in the path. Regardless of the shape of the path, we could define its time functional, which is then going to be given as, well, because the time is s over v, and we could say that this is equal to v over 1 times s, and so we could say that is square root of 2gy over 1, which is v over 1, times s, which is the integral from 0 to x1 of the square root of 1 plus y prime squared d of x. Now, because x here is is what we have used to define this integral, in terms of x here, y is just a constant. And this means that we could input this value into the integral and there would be no change. And so we could say that, well, time then would be equal to this expression over here, whereby we have inputted this value into the integral and combined the root sign, and we have this expression over here, and this would be the time functional of whatever we're dealing with in the Brachistochrone problem. And the point of the Brachistochrone problem and the parameters given in the Brachistochrone problem is basically minimizing time. And we're gonna solve this concept, or we're gonna apply this concept of minimizing time into the Euler-Lagrange equation that you could see in the previous video. And I'm gonna do that now, but before we're gonna do that, we're gonna convert the form of the Euler-Lagrange equation into something that is gonna be easier when we are dealing with a functional as complicated as this, because given that this functional is going to be really hard to integrate, we have to convert the Euler-Lagrange equation into something that is simpler so that we could apply this. And that's what I'm going to do in the next part of the video, which is going to be part 3. Alright, so this is part 3 of the Brachistochrone problem, and it is the Beltrami identity part. So before we move on to the Beltrami identity, what did we do in part 1 and part 2? Well, so far we have, in part 1, we have defined the equation of a cycloid by giving both its x-coordinate and its y-coordinate in terms of given variables, the radius and the angle it deviates from the original circle. And then we have given the time functional of any curve that is given in a Cartesian plane that follows any path in the effect of gravity, and that would be our time functional. And so moving on to the Beltrami identity. But why do we have to find the Beltrami identity? Why can't we just input the time function out into the Euler-Lagrange equation? Well, the main problem is that doing that would be very difficult because the time function that we have here, when we input this function out into the raw form of the Euler-Lagrange equation, it's going to be impossible because we cannot differentiate this here in terms of y or y prime, because it is in itself an integral in terms of x, in terms of the variable x. So we need some way to alter the formation of the alter the Euler-Lagrange equation and then input time into it to get a more simpler version. And in the process of deriving the Beltrami identity, you get to know why using the raw form of the Euler-Lagrange equation won't be possible. And so first of all, let's write down the Euler-Lagrange equation. So we're going to start off with the Euler-Lagrange equation, and then we're going to step our way towards the Beltrami identity. And so we have the Euler-Lagrange equation that and because we are minimizing time, we're going to set time as our functional we're trying to analyze. And we're going to say that the partial of t or partial of y minus d of dx, partial of t or partial of y prime is equal to 0. This is basically the Euler-Lagrange equation in terms of time. And now, first of all, we're going to transform into the Beltramian identity. The first step is going to be multiplying both sides by y prime. And you'll get to know why a few moments later. So first of all, let's just do this. So we have just multiplied y prime to both sides of the equation. And let's look at t. T is a functional that depends on 3 variables, x, y, and y prime. And so what would happen if we differentiate time in terms of x? Not the partial, but just in terms of x. And we're going to, due to the chain rule, we're going to have something that looks like this. So dt of d of x would be equal to first partial t of partial x plus partial t of partial y times y prime. And so the chain rule basically says that if we differentiate something in terms of a variable, we do it in terms of all variable that is present in the functional. But we do it, first of all, we do it x, and then we have to multiply, due to the chain rule, we should multiply the derivative of the variable x. And because that's 1, we don't do anything here. And then when we do the same thing for y, we multiply the derivative in terms of x, which is y prime. And we do the same thing for y prime. And so the derivative of y prime is going to be y prime prime. And so that's going to be the premise. And then we see that we have partial ty times y prime here and partial y prime at here. So we're going to express this here in terms of partial t of partial y times y prime and get this expression. We're going to multiply this first, subtract this first, and then subtract this. So we know that this has to be the case from this equation over here. And then we're just going to substitute this here into here, because they're equal. And so we get, by doing that, we get an expression that looks something like this. Okay, and then we're gonna arrange this so that we could visualize something that I'm gonna do in a few moments later. I'm gonna wrap this and send it to the back of the equation and say that dt over dx minus partial t of partial x, now minus a big bracket, partial t of partial y prime times y prime prime plus d over dx partial t of partial y prime times y prime is equal to 0. It's just basically the same thing. Now when you look at this, it's kind of, you get to see, now when you look at this, you kind of see what I'm trying to do. Because when you see, let's say we have part 1 here and then part 2 here. So y prime we're setting as part 2. No. We can see that this here, d over dx times partial t of partial y prime, is the derivative of partial t of partial y prime over here. And we also see the y prime prime here is the derivative of y prime. So basically what we have is when we say f is equal to y prime, g is equal to dt, no, partial t partial y prime, then we have something that looks like, here it's going to be gf prime plus f and g prime, or g prime of f. We have gf prime plus g prime of f. Now what do we know when we see gf prime plus g prime of f? We know in the product, let's look at the product rule from simple calculus. When we differentiate a function called fg, we know that first of all we differentiate the first part and multiply the second part without doing anything, without touching it. And then we don't touch the first part, and then we differentiate the second part. This is the product rule. And now the same thing could be applied to here. We could say that, well, gf prime plus fg prime, that's equal to fg prime, we just rearrange that, plus f prime g. And so it's basically doing the same thing. This is, no, wait, when we say this first and then this first, we get f prime g plus fg prime. So basically what we're doing, this over here, when we set f as y prime and g as partial t of partial y prime, this would be equal to fg of total prime, which is going to be equal to d over dx of fg. Okay, so then this means that this form over here, we could say that this is equal to d over dx of f times g, which is going to be f, which is y prime, and g, which is partial t of partial y prime. So we get partial t of partial y prime of y prime. This here is going to be equal to that, whereby when you apply the chain rule, we get the first part prime y prime here. So first, yeah, d over dx and prime is basically the same thing. So d over dx of partial t of partial y prime times y prime, which is here, plus, don't touch the first part, so partial t over partial y prime times y prime prime, because that's y prime prime is the derivative of y prime. And so we have this part over here, the big bracket here, we could simplify it into like this, into this form. And we get this equation now is equal to dt over d of x minus partial t of partial x minus d over dx of partial t of partial y prime times y prime is equal to 0. We have this form over here. Now what do we want to do? Now what we want to do is we could spot a shared multiplier. We can factorize this. Let's have some space. So what space can we make? Let's erase the top part. So yeah, we're going to erase the entire top part because that's what we use to derive this form over here, and we're going to continue on with this here. And so we have this form over here, and we see that d over dx, the term d over dx, is being shared in two different areas, here and here. So when we wrap this equation in terms of d over dx, we get, well, first we have t, And we also have minus partial t of partial y prime times y prime, close bracket, and minus partial t of partial x is equal to 0. And now, what do we know about partial t of partial x? Now, we have the time function out here. And saying that we're like taking the partial x, or taking the partial derivative of x of functional, in terms of x of functional t, we're basically considering anything other than x as a constant, which means that we're basically saying that, well, then partial t of partial x is going to be saying that, yeah, because we're basically considering everything else here as a constant, and we don't have the term x here other than dx, which is just a small change, we're gonna have this is equal to 0, because everything else we're considering it as a constant, and there is nothing else here other than y and y prime inside the integral. And so it's basically taking the integral of 0 and then differentiating it, which is going to give us a 0. And so we could say that the partial t of partial x, taking the partial derivative of functional t in terms of x, is going to be equal to 0. And so we could just erase this term here because it's equal to 0. It says equal to 0. Okay, so we have this expression over here. Now what could we do? Well, we're gonna integrate both parts. Integrate both parts. Yeah, we're gonna integrate both parts. And when we integrate both parts, we're gonna do that. And integrating, d over dx, we're basically canceling the differentiation out. So we're gonna get the inside of the differentiation, the inside of d over dx, and get this expression over here. And when we integrate 0, we're going to get some constant called c. And that is the Beltrami identity. We have just derived the Beltrami identity, whereby it states that from the Euler-Lagrange equation, we could derive that t minus the partial derivative of t in terms of y prime times y prime is equal to a constant, because the integral of 0 is going to give us any constant, just any constant. And so that here we have the Beltrami identity, and we're going to write that down here as a record of everything we have done up to this point. And the next part, we're going to use the Beltrami identity and this equation in terms of time, the time function over here, to derive the solution to the Brachistochrone problem. So this is part 4, which is actually solving it now with all these things in so with part 2 here and part 3 here, now we could use these equations to solve the Brachistochrone problem. First of all, let's look at the time function over here. So we have t is equal to 0 to x of 1 square root of 1 plus y prime squared over 2gy times d of x. Now, when you look at my previous video on the Euler-Lagrange equation, we had the expression that went like the f of x comma y when y prime was equal to the integral of 0 to x of 1 of some another functional like this. And from this equation, what we did was plug this into the plug L here into the Euler-Lagrange equation. And so when you do the same thing with this one over here, it's actually we can't say, if we're going to plug this into this form over here, we can't say we're not plugging this big T over here into this equation. We're actually plugging So let's say when we have time taken here, and we're trying to optimize the time taken, then what we're actually doing is saying that, well, the time taken functional, the functional for time taken is equal to the integral of some functional x, y, y prime d of x. And so we could say that the functional time then is not equal to the entire thing over here, but it's actually, because we are giving this as small t, we're saying the time functional that we're trying to plug into this equation over here is going to be given as the inside of the integral, which is given as the square root of 1 plus y prime squared over 2gy. So actually what we're plugging into this functional over here is this equation, this expression, square root of 1 plus, so the inside of the time taken functional is the functional that we are trying to plug into this equation over here. So let's erase all this, and let's do that. We have t, small t, time taken here, which is, and we're taking the inside, inside the integral of the time taken functional, and we're plugging that value in to this equation over here. So we have the time taken functional here, and then the functional for big T that we're plugging in to this equation in order to optimize t, the small t, time taken, into this equation. Okay, so let's do this. Erase this, and we have this in mind. And so what we're trying to do, let's first of all substitute t into this equation. Yeah, so we know what t is. T is basically this expression over here. And so all we have to know is the partial t, so the partial derivative of t in terms of y prime times y prime. And let's do this first and then multiply y prime later. So we're trying to differentiate t here in terms of y prime, the partial derivative of t in terms of y prime. Okay, so this is, we know that this is equal to 1 plus y prime squared. We know that this is equal to 1 plus y prime squared over 2gy of 1 over half. So when we differentiate this in terms of y prime, we get 1 half here. We do the same thing as we would differentiate any square root of x. We get to the power of minus 1 half, and we apply the chain rule, so we differentiate the inside in terms of y prime, and we get 2y prime over 2gy. Because we are integrating the inside part in terms of y prime, only in terms of y prime, considering everything else as a constant because it's a partial derivative. And so we get 1 half times the reciprocal of the square root of this expression. So we get square root of 2gy at the top because we are getting the reciprocal, and we get 1 plus y prime squared at the denominator. And then we're multiplying 2y prime over 2gy. Okay, so we can erase these and get square root of 2gy here. We can cancel the 2 out, and we have the expression that goes as y prime over square root of 2gy times square root of 1 plus y prime squared. And what we have to know is we have to multiply y prime. And so that multiplied by y prime, we get y prime squared over square root of 2gy plus 1 plus y prime squared. Okay, so that's what we have for this. And so when we express all of this in terms of y prime and g and y, we get, well, t as it is, so square root of 1 plus y prime squared over square root of 2gy, which is time here, which is big T here. We're dividing the square root into the denominator and the numerator, and then we're subtracting this value like that, and we're saying that would be equal to a constant called c. Okay, we're just going to erase that too, and erase all that. Okay, so we have this. What are we going to do? Well, first of all, we're going to multiply both sides by square root of 2gy and square root of y prime squared to get the fraction out of the equation. So we get, when we multiply square root of 2gy and square root of y prime squared, we get square root of 1 plus y prime squared times square root of 1 plus y prime squared, because, you know, when we multiply square root of y prime 1 plus y prime squared times square root of 2gy, we cancel the 2gy and we get only the square, we get 1 plus 1 square root of 1 plus y prime squared from the numerator here, and another square root of 1 plus y prime squared from the multiplier here. And then we do minus y prime squared because the new denominator is cancelled out, and we get c times square root of 2gy times square root of 1 plus y prime squared. This is going to be equal to 1 plus y prime squared minus y prime squared equals c square root of 2gy square root of 1 plus y prime squared. So we cancel y prime squared out because it's plus minus, and we get an expression that goes like 1 over c square root of 1 plus y prime squared. We're trying to arrange everything in terms of y prime. So let's say it's equal to 1 is equal to c of square root of 2g times square root of y times square root of 1 plus y prime squared. It's basically the same thing. We're dividing this third here into two forms, and let's square both sides. And so we get 1 is equal to c squared times 2g times y times 1 plus y prime squared. Okay, and then let's divide both sides by c squared over c squared times 2g, because all we're trying to do is get an expression in terms of y prime. We get y times 1 plus y prime squared is equal to 1 over c squared 2g, c being any constant. And because we define c as just any constant, 1 over c squared times 2g is also just any constant. C could have been anything. C could have been any constant that exists, and so c squared times 2g is also going to be any constant that exists in the Cartesian plane, any real number constant. And so we could just say, before we do that, we could just say this is equal to k being just another constant. Or we could just say it's going to be another c, which we could also just say it's c. Let's just say it's c. Although, indeed, 1 over c squared times 2g will not be equal to c. However, because we defined c, because when we were trying to do this, c was basically equal to the integral of 0. Integral of 0 can be any constant, and so c could be any constant, which means that 1 over c squared times 2g also is any constant. And so there's basically no meaning in differentiating c and 1 over c squared times 2g. And so we're just going to say that that's equal to c. And in the future, when we're trying to do something to the constant, maybe we're adding a constant to the constant, or multiplying or dividing a constant to a constant, we're just going to say that it's going to be constant c, any constant c, because c is any constant. Okay. Then we could say that, let's see, y plus y times y prime squared is equal to c. And then we could say that, well, y times y prime squared is equal to c over y. So y prime squared is equal to, c minus y, sorry. And so that would be equal to c minus y over y, which is going to be c over y minus 1. And so we get y prime is equal to the square root of c minus y over, let's just leave it like that. So y prime is equal to the square root of c minus y over y. So y prime is equal to the square root of c minus y over y, where c is any constant real number, any real number constant. And now, what are we going to do in order to solve okay, so we have dy over dx is equal to the square root of c minus y over y. And our goal here is to get an expression. Yeah, our goal is to get some. So we have dy is equal to the square root of c minus y over y of d of x. And so we could say y is equal to the integral of c minus y over y d of x. And when we solve this, it's going to basically give us the equation, the solution to the equation we're trying to find. And in order to do that, we're going to have to use trigonometric substitution in order to solve this integral. And I'm going to do that just now. First of all, there's a mistake I made, which is that from this equation, what we want is not, it's not an equation in terms of y. What we want is an equation in terms of x that is defined in an equation that defines x that is given in terms of y. That's what we want. And so in order to do that, first we're going to get the reciprocal of both sides, and the equivalent sign will still be valid because we're reciprocating both sides. And we can say that dx over dy is equal to square root of y over c minus y. Reciprocal here, reciprocal here. And then we could say, well, that dx is going to be equal to the square root of y over c minus y times d of y, multiplying dy to both sides. And then we could say, when we integrate both sides, we get x is equal to the integral of square root of y over c minus y of d of y. And so we have an equation that defines x in terms of y. Now, what are we going to do now in order to solve this integration that seems quite unsolvable because it's not a form that we are used to do. In order to do this, we're going to look at, it's kind of a cheating method, but it's really not. We're going to substitute y with some trigonometric property, as I said before. But what trig property we're going to use, we're going to get a hint from the answer over here. And the answer here is basically, the equations of a cycloid. And because we're trying to prove that the solution to the Brachistochrone problem will be in the form of a cycloid, when we substitute y, this value, or something similar to this value, y, and then work our way through, get our answer to x, and then when that answer to x matches, the equation here, then it means that because the definition of y and x both matches in this equation that we have derived from the time derivative, the time function out, we could say then that the answer to the Brachistochrone problem is indeed in the form of a cycloid. Because we have used one definition here in order to solve this, and then when we get x is equal to, when we get the answer to x also, then that means that indeed our answer is in the form of a cycloid. And so we're going to do that. But we're not going to use y equals r times 1 minus cosine theta in its raw form, because doing that won't give us the answer. But still we're going to get a hint from, we're going to alter this expression into something that we want to use. Well, we have here y is equal to k times 1 minus cosine theta. And k is just another constant. It's a constant. Because we could use any constant we want, I'm just going to set the constant as k. So we have y is equal to k times 1 minus cosine of theta. Well, let's look at the cosine double angle formula. We have cosine of 2 theta. We know as a fact that cosine of 2 theta is equal to cosine squared theta minus sine squared of theta. And then we could say, then this is equal to 1 minus 2 sine squared theta, because it's basically saying, because cosine squared theta plus sine squared theta is equal to 1, we're subtracting 2 sine squared of thetas from that expression, so we get 1 minus 2 sine squared of theta. And we could divide, the thetas by 2, and still the equivalent sign should be valid. Because basically what we're doing is dividing the angles, all of the angles by 2, and still it should work because this is just an equation that shows the relationship between cosine and sine. And so we get cosine theta is equal to 1 minus sine squared of theta over 2. Okay, and then we could say, then therefore 1 minus cosine of theta should be equal to 1 minus 1 plus 2 sine squared of theta over 2, which gives us 2 sine squared of theta over 2. And because the constant k here we assigned as could be anything, indeed y then is equal to 2k sine squared of theta over 2, because as I said before, k can be any constant. We're going to say, well, then k is equal to 2k. And so we get y is equal to k sine squared of theta over 2. And that's going to be the expression that I'm going to input. I'm going to substitute y. So the thing I'm going to do is substitute y in terms of k times sine squared of theta over 2. So let's erase all that. And keep in mind that this expression over here is derived from the equation we have for a cycloid. And we're going to match if the result for x, if the result for x also matches this form, then we know that indeed the solution to the Brachistochrone problem is a cycloid. That's the point I'm trying to prove. Okay, so y is equal to k sine squared of theta over 2. Okay, then what would dy over dx be? Well, dy over dx, we're going to differentiate this. No, dy over d theta, sorry. Because theta is the new variable we're introducing. So dy over d theta, that's going to be equal to k times sine theta over 2 times sine of theta over 2. Okay, so in order to solve this, we're going to use the chain rule. So differentiating this part, the first part would give us k cosine of theta over 2 times 1/2. So we get k times cosine of theta over 2 times 1/2 times sine of theta over 2, plus we're going to leave the front part now as constant, and we're going to differentiate the second part, which gives us cosine of theta over 2 times 1/2. Now this is going to be equal to, well, we have k here, cosine here, sine here, 1/2 here, k here, cosine here, sine here, 1/2 here. So we basically have two of the same expression. And because we have 1/2 multiplied in each, we just get k times sine theta over 2, cosine of theta over 2. And that would be our answer to dy over d theta. And so we could say that dy is equal to k sine theta over 2 cosine of theta over 2 d of theta. Okay, then let's write this again. X is equal to integral of square root of y over c minus y dy. And we said that y is equal to k times sine squared of theta over 2. And this would give us integral of square root of k sine, I'm going to have to write this larger. So y, which is k sine squared of theta over 2 over c minus k sine squared theta over 2 times dy, which is given by k sine theta over 2 cosine theta over 2 and of d theta. We're going to have something that looks like that. Okay, now what could we do from this point onwards? Square root of c plus, or 3 times c times k. Okay, here we could see that we set k here, we set k as any arbitrary constant, which means that k could be any constant we want to define, as well as c over here. Okay, let's alter c. We set c as any arbitrary constant. It doesn't really matter what we change, but because we have only one c, it's going to be easier to change c as in the form of anything we want. And we could do this because here when we, in the 10 or 15 minutes ago, we defined c as any possible constant because we are giving c as the integral of 0. And so when we say, this means that we could say c as equal to k. It doesn't really matter because c could be any constant. And so let's deal with the special case that c is equal to k. This means that we could change c here as k, and then we could say that this is going to be equal to the square root of k. We could say that that's equal to the square root of k sine squared theta over 2 over k times 1 minus sine squared k. Right. Yeah, so k times 1 minus sine squared theta over 2 times k sine theta over 2 cosine theta over 2 d theta. Now that's going to be equal to, we know that 1 minus sine squared theta over 2 is going to be cosine squared theta over 2 because we have this expression over here that gives the relationship between sine and cosine. So cosine squared theta over 2 is equal to 1 minus sine squared of theta over 2. So we could replace this here with cosine squared theta over 2 because those are equal. And so we have the square root of k sine squared theta over 2 over k cosine squared theta over 2 times k sine theta over 2 cosine theta over 2 d theta, which is going to be equal to, now we could say, we could eliminate the root signs, and we're going to get something that looks like this. So square root of k sine theta over 2 square root of k cosine theta over 2, and these could cancel out, times k sine of theta over 2 cosine of theta over 2 d theta. And that's going to be equal to, cosine and cosine cancel out, so we basically get k sine squared theta over 2 d of theta. And always keep in mind that we have set y as equal to k sine squared theta over 2. So we're basically getting the, okay, let's just look at this for now. And we're gonna have to solve this. Okay, how could we solve this? Well, we could use another trigonometric property which gives so we have sine cosine 2 theta. Yeah, we have cosine. Let's get back to this expression over here, this trigonometric property. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And because we're going to deal with sine theta, we could say that cosine 2 theta is equal to 1 minus 2 sine squared of theta. And then we could say that 2 sine squared theta is equal to 1 minus cosine of 2 theta. And so sine squared theta is going to be equal to 1 minus cosine of 2 theta over 2. So sine squared of theta over 2 is equal to 1 minus cosine theta over 2, which is 1/2 minus cosine theta over 2. Okay, then let's erase all this part here. and say that, well, this expression now is going to be equal to the integral. So x is equal to the integral of k times 1/2. So 1/2 k minus k cosine theta over 2 d theta. Okay, so now that's easy. We have d theta here, so we have 1/2 k theta minus k over 2 cosine of theta, and when you integrate cosine, when you integrate cosine, we get sine, and so we get k over 2 sine of theta plus constant c, and so that's going to be our answer. And here we could say we could wrap all of these expressions by 1/2 k, and we get theta minus sine of theta plus c. X is equal to. And now what do we know? Well, we said y is equal to k. And we said y is equal to k sine squared of theta over 2. And from that equation there, you could say that's going to be equal to k times 1/2. So we could basically do the same thing. 1/2 k minus k cosine theta over 2. So when we wrap all of these by 1/2 k, we get 1 minus cosine squared. So y is equal to 1/2 k 1 minus cosine squared. Now what can we see? We can see, let's take this expression and send it over here. So this we have found by using all of these, the Beltrami identity, the time functional. We have used all this to derive this equation over here. And the equation we got, from the cycloid diagram at the very start of the video, we got x is equal to r theta minus sine theta, and y is equal to r 1 minus cosine theta. And what do we realize about these two here? Well, they're basically the same thing. When we said r is equal to 1/2 k, and c is just a translation in the x, when you get x minus c, then it's a horizontal translation. We basically get both of them as in the form of a cycloid when r is equal to 1/2 k. So we just ensure that k is equal to the radius of the circle we are changing, we're rotating. We get that the solution to the Brachistochrone problem is in the form of a cycloid. And yeah, so this is the conclusion to the video. We have just proven that the solution to the Brachistochrone problem is indeed in the form of a cycloid. And so yeah, that is the conclusion of the video. I hope you liked it. If you liked it, please give me a like button, subscribe, and please leave a comment below if you want to give me any suggestions or improvements I could make. Yeah, I would really like that to happen. Thank you all very much, and see you in the next video.